excited to be here, especially because I am in week 39 of my pregnancy. So I am happy to be here. And let's hope that I will finish my lecture. Yeah. Okay, so first of all, I want just to thank my advisor, Professor Ronnie Neumann, for a really special trip on my research, and also my group, and all the collaborations that help this research. So what we will talk about today, we will try to solve the question how we can reduce the atmospheric CO2 gas in our atmosphere, how to make our environment better by using chemistry. So we all know that CO2 gas is a greenhouse gas in the atmosphere that help us, like other greenhouse gases, to be here in our planet. And the CO2 emission is balanced by CO2 fixation during the years by plants, for example. But since the Industrial Revolution, the amounts of CO2 in the atmosphere is rising. So that's problematic. And you can see here that during the years, this concentration is increased, especially in the last recent years, and it's increased by 50% amount, and that's a lot. So what we try to do in our lab, we need to think about a process how to reduce this amount of CO2 in the atmosphere in order to reduce the global temperature, and this will be done by green energy or green chemistry. So if we look together to the map of the world in 1750, we can see here that most of the world are below 50 million tons of CO2 concentration per year. But if we compare that to the 2020, you can see how this picture is changed and how we have a lot of CO2 concentration. Most of the country are above 2.5 billion tons of CO2 per year. So especially United States, Russia, and China. So in our lab, we decided to look to this simple molecule of CO2. This molecule is linear and very stable, energetic. It's very hard to break it. And what we want to do, we want to pay off some energy in order to break it. Yes, in chemistry we can break molecules. So in order to move from the CO2 to the bent geometry, we need to pay energy. And then if we reach this point, we can also break this bent geometry. It will be easy to break this bent geometry to other materials such as CO, methane, etc., that can contribute to be valuable chemicals for green fuels in the future. So it's important to do that. Why? Because it will open the door to have recycling between the amount of CO2 in the atmosphere and having green fuels in the same time. So in one hand, we will reduce the amount of CO2, and in the other hand, we will make our environment much better. But in order to move here, this hard barrier, we need to use material that's called catalyst. So what is catalyst in chemistry? Catalyst is material that can reduce the amount of energy that we need in order to achieve some reaction, and also make the reaction come true in less time. So if I want to give you some example of catalysts, so we can here compare between the process without catalyst and with catalyst with this man. This man without catalyst need to work hard in order to throw the rock and get the products. And with catalyst, it's much easier, and it will take less time. So the main question that we ask ourselves during the research is how to translate knowledge from biology, enzymes, to chemistry. How to use this magic in biology, in our catalysts, and chemistry. And for that, I just want to talk about some family of enzymes from biology that called the carbon monoxide dehydrogenase. This enzyme has a lot of different metals inside it. One kind of it include into it two metals that I want you to remember, nickel and iron. What this enzyme can do in nature, this enzyme can take molecule of CO, the broken molecule, and convert that to CO2, okay? And in the same time, you also can do the reverse process from CO2 to have CO, the uncommon and this is uncommon process for him. What we want to do, we want to take this uncommon process of nature and make it come true in our lab. So we start to build this catalyst, these chemicals, and these catalysts contain different metals. Here we have some bucket that contain a lot of metals and oxygen. But what is important for me is the surface area of this catalyst. In the surface area, we have we can substitute 3 different metals that belong to iron, copper, and nickel. And we decided in this research to build 2 different catalysts, one with 3 coppers, and one with 1 iron and 2 nickel. And if you remember, the 1 iron and nickel is like the enzyme that we have in the nature. So in order to move from CO2 to the Bell geometry and then to the valuable chemicals, we need catalysts. But beside the catalyst, we need also a source that will help this process come true. In my research, I use the electricity as a source. Especially, it's called electrocatalytic process. And what we have a cell like this, and we dissolve inside it our catalyst with 3 electrodes that we connect to the electricity. And what is important here, that we bubble CO2 inside this cell, and in the end we check which product we succeed to break from this CO2. So what we got, if we look to the process that we want to achieve from CO to CO, to break this molecule to CO by using this catalyst, when we check the first catalyst with the 3 coppers, we succeed to get from all the CO2 that we put in the reaction, CO in efficiency of 98%. And that was not trivial, and that was also a very exciting point in our research. And the interesting thing, when we check the next catalyst, that it contained the iron nickel from, like the enzyme from nature, and we bubble CO2 and we check the products inside the cell, we just found CO2. And that was strange. What happened here? So after deeply thinking here and investigation, we succeed to understand that every CO that we produce from the CO2 here immediately reverse to be CO2 again. And that, of course, can be understood, that remind us the functional model of the enzyme from nature. So we succeed to publish this work recently with the work of, deeply work of, to understand the mechanism of that by using UVVs and Raman spectroscopy. But beside to understand the basic science of this project, our future goal is also to put this project in the industry. And our dream is beside every factory that we have to have process that we have with a lot of CO2, of course, to have process of electrocatalysis by using these special structures and to get from that valuable chemicals that will help us to get green fuels and make our environment much better. Thank you.
Thank you,
Dima, for this inspiring talk. Questions, please?
Yes, from the energy conservation point of view, the step that you break the CO2 for creating methane or CO, and to use that as a fuel, it is actually, well, you need more energy, right, than the energy that you get, because from the energy conservation point of view, because you do something, there was energy lost.
You mean the continuous way from CO and methane to have some fuels in the end?
And then you use that fuel to maybe take energy. So I suppose that you need to put more energy to break CO2 than the energy that you can take from the result.
Amazing, yeah.
So what's the meaning?
Yeah. Amazing, good question. This is the point that we thought now how to make it better, because to break CO2 to CO, we need energy, okay? And we will stop there. And the question, if we can continue to alkanes CH, that will be fuels in the future. And what we try to do now is to do the process immediately, not to stop in the CO, to put energy and to get immediately to our alkanes. That's not easy, and but we hope we will succeed. Yeah. Yes.
What is the rationale behind the design of the catalyst structure itself? Is it supposed to resemble the enzyme?
It's not, but what is unique in this catalyst that it gives you, when we synthesize it without the three metals, like without the cat. And it gives you the opportunity to put every metal or active metal that you want in chemistry in order to open the interaction between these metals and CO2. So I think the beauty in this structure that it's opened and multi-metals substituted, yeah.
Is this enzyme unique for the CO2 molecule, or it can capture other gases also? Because if you want to implement this in the industry, then how you are going to capture only the CO2?
Yeah, this family of enzymes is especially for CO and CO2, so it's unique, yeah.
Have you tried these electrochemical reactions on large scale?
No. This is the point now. We just start to talk with some company. I hope it will work, yeah. We just try in the lab in small scales, yeah. Oh, that's a good question. Yeah, these catalysts can react with other gases, and we have projects in our lab that this catalyst can react with, like producing ammonia from reduction of nitrogen, and also nitrogen can react with that. So it's open. Yeah, it's not just, this catalyst, it's not just for CO2 process. Okay, so let's thank Dima again. Thank you.